Hi, this is Jeff Spence, your Math 135 instructor for the Community College of Denver, and this is our video lecture over 9.3, which introduces the p-value method for hypothesis testing. Now, all the notes in this section are going to be under the context that we're testing the population mean. So we've been doing that for the past 3 sections now, but the big thing here is we're introducing what a p-value is, what it means, how to find it, and how it's used to come up with a conclusion, to reject the null hypothesis or fail to reject the null hypothesis. So the p-value will give us it'll give us an amount of strength of evidence against the null hypothesis, and eventually we will assess that. But the main thing is we want to know how to find the p-value and then how to compute it, by computing it and then figuring out how to use that value to make our conclusion, to reject the null or fail to reject the null. So the p-value is a probability. P stands for probability, and we're going to compare that probability to the other probability, alpha, which is the level of significance. So in 9.2 you saw that we had a table there that used various levels of alpha, 0.10, 0.05, and 0.01. And those are just certain levels of significance. Basically, they're areas under the curve and can also be interpreted as probabilities. So 0.05 would be 5%, 0.10 would be 10%. So the p-value measures how well or poorly the data fit the null hypothesis. So the big thing here is that we compute the p-value, which is the probability of your evidence, basically the probability of observing a sample statistic at least as extreme as the statistic that you got. So in other words, it's the probability of your evidence or anything more extreme if we assume that the null hypothesis is true. So it's that whole idea, well, if the defendant is really innocent, then why were there 5 eyewitnesses who witnessed the crime? Or if the defendant really is innocent, then why do we have DNA evidence matching the defendant to the crime? Those types of things are what we're going to be thinking about. So the method for calculating the p-values will usually use norm CDF, because p-value is just a probability or an area under the curve, and we use norm CDF to find that. And so that's why it's important to know if we have a right-tailed, left-tailed, or two-tailed test, because if we have a right-tailed test, we're going to be measuring finding the area from our z-data into E99. If we have a left-tailed test, we'll be going from negative E99 to our z-data. And if we have a two-tailed test, then we'll do one of the two tails, whether it be negative E99 or positive E99, and then multiplying that value by 2. So the main thing here, just visually, I want you to look at this side on the right, is that if we have a right tail test, the p-value is the area to the right of your z-data. Okay, remember z-data is a formula that tells us how many standard deviations from the mean our sample statistic is. And remember, the idea is the further away z-data is from the mean, the more evidence we have, and thus the smaller the p-value is. And the smaller p-value is, the more likely we are to reject the null. So just showing here that if we have a right tail test, we go from z-data to E99. If we have a left tail test, we go from negative E99 to z-data. And if we have a two-tailed test, depending on what side z-data is on, we go from that side to E99 if it's on the right side, or from negative E99 to z-data, and then we take these two areas together. The quickest way is to multiply it by 2. So a p-value is based on the value of z-data, so you have to compute z-data first. It tells us whether or not z-data is an extreme value. The critical value method was we looked to see if z-data crossed this line in the sand, the critical value. Now we're going to have an easier way, I think generally, is the p-value, where we go from a z-data to finding an area, just like using norm CDF, just like we've done in Unit 2. And it says unusual and extreme values of the sample mean, and if it is an extreme value, then therefore if z-data is an extreme value, then we will have a small p-value. So unusual and extreme values of the sample mean and z-data result in a small p-value, something close to 0, a small area, and values of the sample mean and z-data that are near the center which is not a lot of evidence, result in a large p-value, say greater than 0.15. So remember, the further the distance, the more evidence we have, the smaller the p-value. And the contrary is true. And remember, the smaller the p-value, then we would reject the null. If the values of the sample mean are near the center, we would have a large p-value and we would fail to reject the null. And now we have an exact number to compare to when we're using the p-value. We decide that, well, how small is small for the p-value? Just like before, how big is a big distance for the critical, or how big is a big distance for z data? Well, therefore, back then we had a line in the sand called z critical. Now we're going to take our p-value, which we computed from z data using normal CDF. If it's smaller than alpha, then we reject the null. So we're looking for small p-values. That means that the likelihood of our observation is extremely unlikely if the null was true, so therefore we think the null is false, and we will reject the null hypothesis. That's what this states. If the p-value is greater than alpha, then we fail to reject the null. So here are the steps. This time we do not look up a z-critical. We start with the null and alternative hypothesis. Then we measure the z data, which tells us how far away our sample statistic is from the null hypothesis mean. That'll give us an indication of our evidence, and then to get a solid understanding of our evidence, we'll compute the p-value using technology norm CDF. After that, we'll state the conclusion. If the p-value is less than alpha, we'll reject the null. Otherwise, we'll fail to reject the null. Lastly, we can look at some various levels of the p-value and how strong our evidence is. Generally, the main idea is the smaller the p-value, the more evidence you have against the null hypothesis. Small p-values come from statistics that are very far away from the null hypothesis. So the further we are away, the smaller the p-value, the more evidence we have, and the more likely that the null hypothesis is wrong. That's basically a summary of what's going on here. And there's various values where if we have a p-value less than 1/1000th, we can consider that extremely strong evidence. Somewhere in here is very strong to solid to mild to slight. Once you get to slight evidence, it's above 0.10. Anything above 0.15 is really no evidence to speak of. So that's it for this p-value lecture. We'll work on examples when we see you in class. See you then.